Let's continue with more examples of groups. To do this, let me quickly review the concept of an injection, surjection, and a bijection. So let's start with this definition here, which I have written at the bottom. Let x and y be sets. And then a function f from x to y is called a surjection if the range of f is y. In other words, sometimes people say if every element of y is hit by f. So that means that for every element of y, there exists an element x in x such that f of x is equal to y. So in other words, the range of this function is the entire set y. What is an injection? An injection is a function where two distinct elements of x are mapped to distinct elements of y. So if I take two different elements of x and see where they go, they're not allowed to go to the same element. So distinct elements are mapped to distinct elements. That's what an injection is. More formally, that means if I take any two x1 and x2 in x, then whenever f of x1 is equal to f of x2, that means that the elements were the same to start with. Yet, in other words, if these elements were not the same, then f of x1 is not allowed to be equal to f of x2. So that's an injection. You might know these under different names. Sometimes a surjection is called a function that is onto, and an injection is called a function that is one-to-one. There are also adjectives from these two. We sometimes say that a function is a surjection, a noun, or we say that a function is surjective, an adjective. Same with injection. You can say a function is an injection or that it is injective. Finally, a function that is both injective and surjective is called a bijection, or in an adjective way, you can say that f is bijective. So here's just a schematic look at injection, surjection, and bijection. So the set x here consists of three letters, a, b, c, and the set y consists of four letters, w, t, v, and z. And my function f maps a to w, b to v, and c to z. Is it an injection? If I take distinct elements like a and b, they are mapped to different elements, w and v. B and c are also not mapped to the same element, and a and c are also not mapped to the same element. So different elements are mapped to different elements, so it's an injection. It's an injection. But it's not a surjection, because the range of the function, which I'm going to draw in this sort of orange color, the range is just this. So you see that t is left out. So the range is not equal to y. So it's not a surjection. This function, where x is a, b, c, d, and y is w, v, and z, is actually an example of a surjection that is not an injection. Note, the range now is everything in y, right? W is hit by a, v is hit by b, and z is hit by c and d. So everything is hit by something, not like here when t wasn't hit by anything. So it's a surjection, but it's not an injection because these two elements, c and d, are mapped to the same element. Different elements do not go to different elements, they go to the same element. So it's not an injection. Finally, this is an example of a function that is both an injection and a surjection. Clearly it's an injection because different elements, a, b, c, go to different elements, v, w, and z. And everything is hit here, right? The range is everything. This is the range. Range of h, and this range is equal to y. Same here, right? The range is everything. Range of g is equal to y. So this is an example of a surjection and an injection at the same time, so it's a bijection. One important thing about bijections is that they sort of pair elements in both sets, which means I could define something called the inverse function, namely a function whose arrows go the other way. So if I define these blue arrows here as going the other way, then I have defined the inverse function. Let's write this down actually. So if f from x to y is a bijection, then there exists a function which I denote by f inverse from y to x, such that if I compose with inverse with f, then let's see, f takes me from x to y, and f inverse takes me back from x to x. Sorry, from y to x. So this composite is a function from x to x, is the identity id x on x. And if I first do f inverse, so I go from y to x, and then by f from x to y, I get a function from y to y, and this is the identity idy on y. In other words, f inverse undoes what f does, or f undoes what f inverse does. Pictorially, that just means that you're reversing the arrows. Maybe I'll just do one example here. If I take f from the positive real numbers to the positive real numbers, defined as f of x is equal to x squared, this is actually a bijection. Because two different positive real numbers, when I square them, give me different positive real numbers. And on the other hand, every real number, positive real number, is a square of another positive real number. So the function is both injective and surjective. And what's the inverse function? In this case, a function from R to R, f inverse of x. It's just square root of x. Note that this makes sense because we're talking about positive real numbers. So this is my example 1. Example 2, I can just look at numbers 1, 2, 3. And go from same numbers 1, 2, 3. And I'm going to write something like this. It's brackets 2, 3. Okay, don't worry about what that notation means, really. We're going to talk a lot about this kind of notation. And I'm defining this function the following way. So the function 2, 3, when I evaluate it at 1, it just gives me 1. 2, 3, when I evaluate it at 2, it gives me 3. And 2, 3, when I evaluate it at 3, it gives me 2. Okay, so the notation 2, 3 just essentially means you switch 2 and 3. Okay, so that is this f here, right? It's not just two numbers, this is my function. It's like f. This thing is f. So f of 1 is 1, f of 2 is 3, and f of 3 is 2. Right, so that you're not... Okay, so this is also a bijection. Surely different elements go to different elements. 1 goes to 1, 2 goes to 3, 3 goes to 2. And it's also surjective because the range of this function, f, is, again, the set 1, 2, 3. So f is a bijection. And what is f inverse? Well, let's see. F inverse, that's sort of reversing the arrows, right? 1 went to 1, so under F inverse, 1 also has to go back to 1. 3 has to go to 2, and 2 has to go to 3. So, okay, so F inverse of 1 is 1. F inverse of 2. 2 should go back to 3. And F inverse of 3 should go back to 2. Oh, but look, that's exactly the same thing that f does. So f inverse is equal to f in this case. Okay, so why am I talking about functions? In particular, why am I talking about bijections? Because sort of the bijections are what really interests me. So here's my example of a group. Let X be a set. Okay, and let S sub X denote the set consisting of all bijections. F from X to X. Okay, all bijections from X to X. So I claim then Sx together with, or let me just use the following terminology. Sx is a group under composition. What does this mean, the syntax under composition? Is a group under composition. So that means that this thing is a set and the operation is composition. So that makes it into a set with a binary operation, the operation being composition. Okay, and I claim that that's a group. All right, well, let's check a few things here. So first of all, is this really a binary operation? So if I take a bijection and I compose it with another bijection, do I get a bijection? So this is something, exercise 1. Show that if f from x to x and g from x to x are bijections, then so is f composed with g. So if you compose bijections, you get a bijection. Now, pictorially, that's kind of clear. Because if I take a set X, and suppose that my set X consists of elements A, B, C. All right? X, this is X. And then I'm looking at some bijection, but it has to be X again, right? Because it's from X to X, so it's not a different set. So it's also A, B, C. Okay, so bijection. Let's think about it. Let's think of a bijection between these two sets. Okay, I'm going to send A to A. I'm going to send B to C. And I'm going to send C to B. Okay? So that's my G. I should do G first, right? Because when you compose like this, under composition, the first thing you do is the second function. All right, and now I'm going to do some other function. So again, but it's still the same set X, A, B, C. And I still want a bijection, right? This is a bijection. Different elements go to different elements, and the range is X. So maybe now some other really nice color here. I have a pink. Pink seems really nice. How about A goes to C, B goes to A, and C goes to B. Is that a bijection? Let's call this F. Is this a bijection? Well, different elements, A, B, C, go to different ones. Yeah, A goes to C, B goes to A, and C goes to B. And the range is again the entire set X, so it's a bijection. So what about if I compose these two things? So what's, let's just compute that. So what's F composed with G of A? So I first do F, so first do G, that maps A to A, and then A is mapped to C, so that's C. F composed with G of B, so first G maps B to C, And then f maps c to b, so that's b. And finally, what's f composed with g of c? C is mapped under g to b, and then all the way to a. So this is a. You see, it's a bijection again, right? And the point is, sure, it must be a bijection sort of from the picture. Let me not say any more of this. In any case, picture doesn't prove anything, of course. It's just a particular situation, particular example, particular function. So I want you to show that this is true in general. So once we know that that statement is true, we know that the set of bijections is closed under composition. So that means composition defines a binary operation. So composition of functions, of bijections, defines, of functions, composition of functions, defines a binary operation on Sx. Exercise number 2. What else do I now need to know to show that this is a group? I need to show that this operation is associative. And this is true in general. Show that composition of functions is associative. This has nothing to do with bijections. If I take any functions, f from x to y, and g from y to z, and then h from z to v, then f composed with g, I have to be careful, so I have to go from this direction, right? H composed with G composed with F. Let's see that this makes sense. F takes elements from X to Y. So now G makes sense, takes elements from Y to Z. So G composed with F is a function from X to Z. And then H takes elements of Z and maps them to V. Right? So this whole thing here is a function from X to V. Right? And I claim that this is the same thing as H composed with G composed with F. And so this here, right, would be a function. Let's see, G goes from Y to Z and then from Z to V, so that's a function from Y to V. And this whole thing, so F maps elements from X to Y, and then you apply a function from Y to V, so you get a function from X to V. All right, so both sides define a function from the same set X to the same set V, but now you have to show that for every element of X, they are actually true. So they're actually equal, right? So you need to show that. For all X in X. Okay, let's keep going. So, given these two exercises, I know that S of x is closed under composition, and that composition is associative. What else do you need for a group? You need the identity. So, what would be the identity in this case? So I need a function. Need a bijection G from X to X. Actually, it's called E. E from X to X, such that E composed with F is equal to F composed with E is equal to F for all bijections F from X to X. But so what would be such a function? The identity. Right? What's the identity function, right? So identity function on x takes any little x, this is big X, takes n a little x and maps it to x for all x and x. Right? Because, so f composed with e, if I take any element little x of big X, then e of little x is that x back. So I get here f of x. So this is the same as f of x, right? And here the same thing. So if I take, let's just write this anyway. So I have e composed with f of x, that's e of f of x. But e maps every element back to itself, so that's the same as f of x. And similarly for that. So that's f of e of x. But e of x is x, so that's f of x. So that thing here checks out. Finally, what would be the inverse? So now I also need, so given any f from x to x, I need g from x to x such that f composed with g is that identity. And it's also g composed with f. Right? That's what it means to be an inverse to an element in a group. It's f group operation g, in this case the group operation's composition, should give you the identity. And the identity in the group is the identity function. How do I know I have such a g? Well, that's what we just talked about. Bijections have inverses. So take f inverse to be, take g to be f inverse. This means the inverse function. So it's a function that reverses the arrows. So just to recall, right, we take any set x and we look at all the bijections from x to x. It turns out that when you compose two bijections, you get a bijection. So that defines a binary operation on the set of these bijections. Secondly, composition of any functions is associative, so composition of bijections is, in fact, associative as well. Then there's the identity, namely the identity function, the function that maps every element back to itself. If I compose such a function with any bijection, I get that bijection back. And lastly, every bijection is an invertible function, which means it has an inverse function. So something that satisfies that property here. So that makes this set into a group. And there are some very important examples for which we're going to spend a lot of time in this class studying. And that's the case when x is a finite set. So suppose that x is a finite set. X is a finite set with n elements. Then we write Sn for Sx. Okay, well, you might say, whoa, hold on, but this depends on the set X. There could be many different finite sets with the same number of elements, n, so you shouldn't just use the same notation for all these different sets. Yeah, I agree. So, for now, let's just say that this is in fact, it doesn't matter, but let's just say, suppose X is a finite set with n elements, n elements, and these n elements are 1, 2, are the numbers 1, 2, all the way through n. In fact, you'll see that it doesn't really matter. You can take any elements with any set with n elements, and you essentially get the same group. So then we write Sn for Sx. This is called, Sn is called the symmetric group. on n letters. The symmetric group on n letters, you might say, why on letters? These are numbers. Yeah, that's sort of a historical coincidence that these things are called symmetric groups on n letters. Probably would be better to call them the symmetric group on n numbers. So its elements, the elements of this group are not these numbers, right? They are bijections from this set to this set back, and the operation is composition. And two more remarks here. Bijections on a finite set often have a different name, and they go by the name permutations. So you might sometimes think here that these things are permutation groups. So bijection on a finite set is the same as permutation. And secondly, so many of these groups we looked at so far were abelian groups. But here, the operation is composition of functions. And as you must well know from other areas of mathematics as well, if you compose two functions from the same set to the same set, but in two different orders, rarely do you get the same thing. Rarely do you get the same function. So in general, these groups are actually non-abelian. So you'll see that if n is greater than 2, Sn is not abelian. If you want to know more about these groups Sn, so I'll tell you, hold your horses. We're going to get to them later in our study of groups.